Hi and welcome to this Leaving Cert Higher Level Applied Maths video. In this video, we're going to look at difference equations. Specifically, we're going to look at one question, which was from the higher level SEC sample paper, question 1, and it's part B. This question relates to homogeneous difference equations. If you want to revise the method and how to approach these questions in general, I've linked that video in the description below. So this question often causes problems for students given in how it is presented. It is quite wordy, we have to come up with the difference equation ourselves, and it can be quite challenging to even understand what's going on. And this is a sample paper, so it was never asked in an actual exam. So it is a nice one to examine in your own time, to have for study. We've seen multiple questions asked on actual exams since then, and they've been much more straightforward. So a gardener plants a new fruit tree, which has 3 new branches. In a branch's first year of growth, it will not produce any additional branches, and each branch will produce 1 additional branch every year after that. Okay, so we need to wrap our heads around what's going on there. So the gardener models this growth pattern by defining UN to be the number of branches on the tree n years after planting, with U0 equals 3 and U1 equals 3 as well. So let's see if we can make sense of this. I'm very visual, so I like to see what's going on. So imagine we have our tree and they have planted it, and there are our 3 lovely branches. So this is the start. And then we get to year 1. So when we say year 1, we really mean the end of year 1. So 1 full year has happened and we still have 3 branches. And the reason we have 3 branches is because, going back to this sentence here, in a branch's first year of growth, it will not produce any additional branches. So then we move into year 2. And at the end of year 2, we will now get growth on each of these branches. So now we have 6 branches. And then the following year, which is going to be year 3, each of our original branches, so the blue ones, will produce a new branch because they produce 1 every year. However, the green ones won't, because the green ones are only a year old. And remember, go back up here, in a branch's first year of growth, it will not produce additional branches. So what we end up with is, in year 3, try get another color. In year 3, we have all of year 2 branches plus year 1's will now produce an additional branch. So for year 3, we're going to have what we had in year 2, which was 6, plus the ones we had originally, which was 3. So that means in year 2, that means we had the blue and the green, which were 6 branches. And in year 3, we had everything we can see now on the picture, which are 9 branches. Now, that's great to get us an answer, but we need to try and make sense of this in order to create a difference equation, which is what we're asked in part 2. So I'm going to get rid of this visual for a second, and I'm going to try and write this in terms of our U. So the number of branches in year 2, which is U2, what we're being asked for, will be the number of branches in year 1, U1, because they're all still going to be there, plus each branch that was there 2 years previously, so for us that's year 0, so the start, will produce an additional branch. So what you need to think about is everything that was there last year is still there, plus anything that's over a year old, so really 2 years plus, is going to now produce a branch. And that gives us U2 is equal to U1 plus U0. Now, for us in U1 and U0, they were both 3, so that gives us our 6 branches. Now, for U3, we can use the same logic and say, well, U3 will be all the branches we had in U2 plus everything that was there 2 years ago, so that was in U1, will produce extra branches. So that gives us 6 plus 3. So 6, because that was our answer for our U2 here. So U2 was 6 plus our branches from 2 years previous, which are now going to produce extra branches, which are 3. So that gives us 6 plus 3, and that gives us our 9. So there are 2 answers. And then this method, and kind of looking at it this way, first of all, confirms what we did with our diagram at the start, but also is now written in a way that we can use to figure out what will be our difference equation for un plus 2. So we know that u2 is equal to u1 plus u0, so we can generalize that to say un plus 2. So whatever we have, the number of branches we have now is equal to un plus 1, so the branches that existed in the previous year, plus every branch that existed 2 years before are now going to create new branches, which is going to give us plus un. So that un is not saying that we have to add in those years or the branches that existed 2 years ago. We're saying that the number of branches that existed 2 years ago will now all produce one more additional branch, so that's still going to be equal to the number un. So now that we have this difference equation, we're being asked to solve it. This is a second order homogeneous difference equation. Second order because we start with the un plus 2 and our lowest is un, so the difference there is 2. If you look at your subscripts, you can see an n plus 2 and an n. The difference is 2. So we're going to go through our steps of this. Since we're only looking at this question, I'm going to bring in the steps one by one. Like I said, these steps, we go through them in a lot more detail in the video linked below. So step 1 is to find the characteristic quadratic equation. So that means changing what we have, our u's, into x to a power, so into a polynomial. So the biggest power of x is going to be our un plus 2. So that's going to be x squared. Then our un plus 1 is our x, and then un is our constant. So that's x squared equals x plus 1. Step 2 is then to solve this quadratic equation. So in order to solve it, we want to bring everything to the left-hand side and let it equal 0. Now, the bad news is this cannot be factorized. There are no factors of -1 that will get us to -1. And the only factors of -1 will be -1 plus 1. And that will give us nothing in the middle, meaning we're going to have to use -b to solve this equation. So when we solve this equation, we get this answer, 1 plus or minus square root of 5 all over 2. So I'm going to leave this in third form. That means it's accurate. If we were to put it into decimal form, you'd have to leave enough decimals to make sure you're not upsetting it too much. Usually there is no issue within the exams about how you leave your answers. I find thirds are a little bit easier to deal with. I'm not a huge fan of decimals, but if you are and think it will be much easier to do this question with decimals, absolutely. So I've just pulled in our U0 and our U1 because we're going to need it for this part. But step 3 says use the difference equation theorem 1 or 2 depending on the root. So depending on what our roots are. So the options are we have our different root theorem and we have our double root theorem. So for us we have x equals 1 plus or minus root 5 over 2. There are 2 distinct roots. So we're going to use that difference root theorem. So that means Tn is equal to L alpha to the power of n plus m beta to the power of n. The letters you use to stand for things here does not matter. So I'm using alpha and beta for my roots. So alpha is going to be 1 plus root 5 over 2. Beta is 1 minus root 5 over 2. And then L and M are my coefficients. So when I sub this in, remember we're dealing with U, so we get UN equals L times 1 plus root 5 over 2 to the power of n plus M 1 minus root 5 over 2 to the power of n. So that is our answer. We just now need to find L and M. To do that, we're going to sub in 2 values of n and solve the simultaneous equations for L and M. So the 2 bits of information that we have from earlier in the question are U0 equals 3 and U1 equals 3. You are welcome to use U2 and U3, but they're going to be bigger numbers, so a little bit trickier to work with. So let's work with this. So U0, what that means is we get L 1 plus root 5 over 2 to the power of 0 plus m 1 minus root 5 over 2 to the power of 0 equals 3. Anything to the power of 0 is 1, so this gives us very nicely L plus m equals 3, and that becomes equation 1. Now, let's do the same for u1. So that's L 1 plus root 5 over 2 to the power of 1 plus m 1 minus root 5 over 2 to the power of 1 equals 3. That power of 1 isn't doing anything. So first thing I'm going to do is I'm actually going to multiply across by 2 to get rid of all those fractions. So that gives me L 1 plus root 5 plus m 1 minus root 5, and that equals 6, and that becomes equation 2. So you might feel that it's very complicated to work in surd, and that's absolutely fine. Like I said, if you do want to go to decimal, just be careful you leave enough decimal places that you're not losing too much accuracy. I'm not going to multiply out these brackets because it's going to be easier to think of the brackets like a coefficient of L and a coefficient of M. So we need to figure out how we would make this eliminate. If they're decimals, it should be a lot more straightforward. So I'm going to stick to surd form. So I'm going to make the m's disappear. I'm going to eliminate I'm going to eliminate the m's. And to do that, I'm going to multiply by minus 1 minus root 5. And I do that to the whole top equation. So what that's going to give us then is minus L 1 minus root 5 plus, well, it becomes a minus as well. So a minus M 1 minus root 5. You're welcome to write these brackets in front. Like coefficients, that's fine. Whatever way is easier for you. Remember, multiplication is commutative, so the order does not matter. And then we have plus m 1 minus root 5, and that equals 6. So we can see now be very careful, this m bracket 1 minus root 5, I have a positive and a negative, so they undo each other, they eliminate. The L's do not. Be so careful. So what we have here is we have L times 1 plus root 5 minus L1 minus root 5, and that all equals to 6 minus 3, 1 minus root 5. The reason I put the bottom line first is I don't like starting with my negative. So rather than writing minus L bracket 1 minus root 5 and then a plus L, I just flip the order of them. So this is my equation, and we're going to solve this now for L. So just giving us a bit more space to work. On the left-hand side, we want to get L equals and then everything else on the right-hand side. If you feel more comfortable, you are welcome to multiply out those brackets. However, a quicker way would be to pull out the L, think highest common factor, and that would leave us with 1 plus root 5 minus, use your bracket here because that minus has to affect both pieces, and minus 1 minus root 5. Again, let's multiply out this side. So we'll do a little bit of cleanup over here. This will give us 3 plus 3 root 5. So that tidies up nicely. Here we have our L times. We have 1 plus root 5 minus 1 plus root 5. Minus 1 plus 1 gives me 0. So that leaves me with plus root 5, which is 2 root 5s. And that equals to 2 plus 3 root 5. To get L on its own, we're going to divide by 2 root 5. And then into your calculator, we can put this. The calculator will automatically rationalize that denominator. So turn it into a rational number, so not a surd. And that gives us 15 plus 3 root 5 over 10. Or if you prefer it to be in decimal, 2.17, and it's 0.1708. So I'm just going to stop at 17. So then if we go back to our first equation that we had, that was L plus M equals 3. So we have L as 15 plus 3 root 5 over 10 plus m equals 3. So m is going to be 3. Take away. Now watch this whole fraction. Use brackets if you need to. You're subtracting that whole thing. And then we do 3 minus your previous answer, and we get 15 minus 3 root 5 over 10. And in decimal, that gives us 0.829, going an extra decimal place there because in the last one it was 2.170. So you can put your answer back in third, or you're welcome to do it in decimal. It doesn't matter. So let's write down the solution for Tien. So it looks like this. I put it in decimal, but you're welcome to put it in third either. So the final part of this question is one that if we can get through the previous 3 parts, even students find this one even more challenging in what it's asking. So let's try and make sense of it. So I've just put the original question in there. I've also put in our calculations from part 1, which were U2 and U3. And part 4 asks us that plants must be cut back regularly to allow them room to grow. How many of the old branches should be removed at the end of year 4 to ensure that there are exactly 14 branches at the end of year 5? Okay, so let's start this off in the most sensible way, which is to figure out if nothing happened, what would our total number of branches be at the end of year 5? So in order to do that, we need to first work out U4. So U4 is going to be U3 plus U2, which works out as 15. And then U5 is going to be U4 plus U3, which is 24. So we want exactly 14 branches. Okay, so you want exactly 14 branches at the end of year 5. And there's currently 24. So basically there's 10 extra branches there in year 5 that we don't want. Now, your gut instinct might be to say, okay, great, we get rid of those 10 branches. However, we need to make sure that we take into account that we're cutting at the end of year 4. So we need to look at U4. So in order to deal with that, we need to remove 5 branches, and these branches must be older branches. So they must be branches that are producing other branches, because if we remove 5 of them, we're also removing the 5 branches that they would have produced at the end of year 5 as well. So we're basically saying, right, so let's get rid of 5 older branches at the end of year 4. So that leaves us 10. And that gives us then for U5, the 10 branches that are there plus the 5. Now, the reason we were adding 9 is because there was 9 older branches. Okay, so I'm looking at this 9 here. There were 9 older branches the year before, but because we got rid of 5, because we cut back 5 mature ones, it means that there's only going to be the 4 left. So only 4 older branches are left to produce those additional branches. That gives us our plus 4, and that gives us our 14. So the final answer is we remove 5 branches. So really try and make sense of this. Like I said, this is a great question for your study, for your revision, to practice with. It may not be the nicest one that we could get if we had an exam situation, but we don't have an exam situation here. We have time to process it and to make sense of it. These questions, for difference equations, the methods are so straightforward. The only thing that can catch us out is the wording, the situation, how we're presented with the information. So once you have your method and you're very happy with your methods for first order, for second order homogeneous, second order inhomogeneous, then really focus on going back over the questions again and again and making sense of what they're asking, making sense of the words, and so on.